Welcome to this explainer. I'm Warunika Hippola, and today we are stripping away the abstraction. We're moving all the way from high-level software theory right down to bare metal hardware control. If you've ever wondered how lines of code physically interact with the real world through electrical signals, you are in exactly the right place. Let's get into it.
Here's our roadmap for today. We're going to cover the language of machines, finding data, inside the PIC16F84A, memory and registers, writing the code, and finally, calculating perfect delays.
Okay, let's kick things off with Section 1, the language of machines. So to bridge the barrier between human logic and machine execution, we use a pretty wide spectrum of programming languages. Because at the end of the day, computers definitely don't understand English, right? They only speak binary. Now, on the left side, you've got high-level languages like Java and C++. These are much closer to human speech, and they're machine-independent, which is great, but it means they rely on heavy compiler abstraction to translate what you want into something a computer can actually run. But look at the right side. Low-level assembly language gives us total, unabstracted, direct control over the specific memory locations of a specific processor. Assembly just relies on these handy abbreviations, we call them mnemonics, to represent individual binary machine codes.
Imagine you're writing this out on a whiteboard. Every single assembly instruction breaks down into these four logical components to tell the machine exactly what to do. First up is the label, like start, which acts as a handy reference point in memory. Second is the opcode, or the mnemonic, which defines the actual task, like add or move. Third is the operand, which basically tells the processor the exact data or address it needs to apply that task to. And fourth, the comments. The machine completely ignores these, but they are absolutely vital for us humans reading the code.
Moving right along to Section 2, finding data, specifically addressing modes.
Once an instruction is said, how does it actually locate the data it needs to process? Well, we use addressing modes. Think of these as different kinds of treasure maps pointing the processor directly to what it needs. For example, direct addressing gives the exact memory address of the operand right there in the instruction. Immediate addressing? That skips the memory search entirely and just gives the processor a literal numeric value to use on the spot. And implicit addressing doesn't even need to point to a location because it inherently targets the processor's primary accumulator. So each mode is just a tailored tool for finding data as efficiently as possible.
Now for Section 3, inside the PIC16F84A.
All right, let's step away from this software for a second and meet the actual silicon itself, the physical PIC16F84A chip. This is a foundational 8-bit microcontroller, and honestly, it's the perfect learning tool for embedded engineering. It features a highly streamlined set of just 35 assembly instructions. But don't let that fool you. Surprisingly, it is an absolute powerhouse. We're talking about processing 5 million instructions per second out of just 18 pins. No joke.
Zooming inside that little chip, we can see its internal map. Notice how the program memory and the data memory are entirely separate blocks? This is what we call a Harvard architecture. Because program memory and data memory have their own separate buses, the CPU can actually grab an instruction and access data during the exact same oscillator cycle. So absolutely no traffic jams. It makes execution incredibly fast.
Next up, Section 4, memory banks and registers.
To physically manipulate the pins on the outside of the chip, say sending a voltage to turn on a motor or light up an LED, we really have to understand how it organizes data memory on the inside. The memory is partitioned into two distinct areas, Bank 0 and Bank 1. These hold our special function registers, which control the actual hardware peripherals. To access different registers, we have to toggle a specific bit inside the main status register. This bit literally flips the chip's internal focus between Bank 0 and Bank 1. It's kind of like flipping pages back and forth in a ledger book.
Now, the absolutely crucial piece of the puzzle here is the W register, which stands for the working register. It acts as a universal turnstile for the entire chip. You literally cannot write a value directly to a file register. It's impossible. Instead, your data must pass through the W register first. So you move your value into W, and then you push it from W into your final destination.
Let's put this into practice with Section 5, writing the code, specifically an LED blink.
Let's build up our practical knowledge by writing some real assembly code to blink a physical LED connected to the chip's porta pins. Before we can light it up, though, we have to configure the hardware by following these exact logical steps. We use a register called TRSA to decide if a pin is an input or an output. But here's the catch. TRSA is located in Bank 1. So step 1, we go to Bank 1.
Step 2, we set TRSA as an output. Step 3, we return to bank 0 where the actual Porter register lives. And Step 4, we send a high electrical signal to that port.
Check out how cleanly this logic translates into assembly code. First, we set the status bit to access bank 1. Then we move a hex value of 0 right into our W register turnstile and push it out to TRSA, which establishes the pins as outputs. We then clear the status bit to move back to bank 0, move a literal hex value of 1 into the W register, and push it directly to PORTA. And just like that, the port goes high and boom, the LED turns on.
Finally, Section 6, Calculating Perfect Delays. Okay, so we just turned the LED on. But remember what we said earlier? A microcontroller executes millions of times a second. If we just told it to turn on and off, it would be an invisible blur to the human eye. To actually see the blink, we need to purposely slow the processor down. And we do this by trapping the chip in a holding pattern, a loop, counting down from a specific value before moving on to the next task.
So how do we measure that time mathematically? Well, the chip takes the external oscillator frequency and divides it by 4. So if we wire up a standard 4 MHz crystal, we divide that by 4. This means a single, standard instruction cycle takes exactly 1 microsecond to execute. It's so precise.
To build our delay loop, we use this really ingenious instruction called DECFSC. That stands for Decrement File Register, skip if 0. It takes exactly 1 microsecond to subtract 1 from our counter. But crucially, when it finally hits 0, it skips the next line of code to break the loop. And that skip action actually takes 2 microseconds.
By loading a specific decimal value, which we'll call R here, into a counter register, we can calculate the exact duration of our delay loop. The math is beautiful. The total delay equals 3 plus 3 times R, all multiplied by our microsecond instruction time. By simply changing R, we dictate the processor's execution speed right down to the microsecond.
Understanding how to bridge the gap from abstract software syntax to the exact mathematical timing of electrical signals. That is what unlocks the true magic of embedded engineering. You're no longer just writing programs, you are orchestrating hardware. So what physical systems will you control now that you have absolute cycle-by-cycle command over bare metal silicon? It's definitely a powerful question to ponder. Thank you so much for joining me for this explainer, and I really hope this sparked your curiosity to go out and build something incredible.